Are we recording?
It's a joke, get it? Now, why did I include that? Because it's exactly what we talked about yesterday. Notice in the problem, the dn is identifying the variable. What's the variable? N. And therefore, everything else, whether it's a number or a letter, or in this case letters, they all become a constant. And when you take the integral of a constant, you get the constant times the variable. So that would be s per in. But you got to remember the plus c because it's an indefinite integral. Pretty proud of that. Thanks. Cheers. All right. So we talked about this a little bit yesterday, but I want to delve into this a little bit more, and that is the concept of an integral being a accumulator. So, for instance, in a problem like this, we would say that g of x is defined as the integral of f of x dx from, oh, I don't know, some number. Let's say 0 to x. So, for instance, what would g of 0 be? 0. Hot diggity. What would g of 3 be? 7. 1, 2, 3, 4, 5, 6. 2 halves, 7. Okay. How about g of 7? Ooh, not so easy. Actually, it is pretty easy. Come on. 7. Notice. This triangle, same as this triangle. Oh, yeah. Cancels each other out. Save yourself some hassles. 1, 2, 3, 4, 5, 6. 2 halves, 7. Okay. And again, as we move from the left to the right, we're accumulating area as we move further and further over. And then, of course, you could go all the way to 9. Or you could change the problem, and instead of starting at 0, you could start at something like 2. And then start doing a whole bunch of things like that. So if we start at 2, let me change color so nobody gets confused. And erase this. All those dots. Go away, dots. Okay. So if this is 2, then what's g of 0? -4, very good. Because we're going backwards. So I would have to turn the integral from 2 to 0 into the integral from 0 to 2 and stick a minus sign in front of it so you calculate the area, put a minus sign on there. G of 3, so this is, what did we say, -4? And then G of 7. Is it 3? Because it still cancels. Okay. We good? Nothing. Next on the agenda, another quick note. The difference between velocity and displacement, which I believe we've talked about already, have we not? No. We have not?
A little bit.
Maybe. Well, let's take a look, shall we? If you have the velocity and you'd like to find the displacement, before I go any further, do you all understand that, forget about the math, do you understand the difference between the terms displacement and total distance? Anybody know? So we're all good. Beautiful. Okay. Mathematically speaking, if you have the formula or the function for the velocity, you can find the displacement by simply taking the integral of that velocity. So it's, again, the concept of going from a function to a quantity. What's the quantity here? It's a distance. Feet, meters, miles, whatever. Excuse me, the one on the right is the total distance that you travel. So if you're cha-chaing, you move forward and you move back, and you move forward and you move back, and you move forward and you move back, your displacement would be 0, but your total distance would be the distance that you move forward and back. Okay, doke. The way to remember that, by the way, is consider that the absolute value is going to take a negative distance that you get, like in physics when you talk about distance having position, it takes those negative distances backing up and turns them into positives so that you can add it to the total sum. Okay? Good. Mean value theorem for integrals. Easy peasy. I'm going to try to keep this as simple as possible. It's the concept first that we need to talk about, and it looks something like this. Let's suppose I have a glass full of ice. You can read that, please. To yourself. Let me know if you need help with any words. Okay, we good?
Yes.
Beautiful. So that's what we're starting with. We're going to take that concept and translate it into a function. And it looks something like this. So here's my function. It doesn't matter what it is. But the function is considered the ice. So the red is the scraggly ice in the cup. The cup would be the glass would be the interval A and B. So the blue vertical bars are the sides of the glass, and the red is the function inside the glass. As that thing melts, it will level out at a certain point. That leveling out point is what's called the average value, and it's commonly referred to as f of z. So understanding this whole averaging out thing, if this is actually the averaging level, then this space up on top should equal this space on the bottom. I don't think I did a very good job of showing that, but it's probably not the exact average area. But all the points above the average value will come downward, and all the points below will come up, and they're going to meet at that average value. So that's the f of z. That's the y value of the average value, the level of the water in the glass. We're going to be finding two things. One is the level of the water in the glass, and the other one is these points where the function hits that level of water, the average value. Okay, and we commonly call that z. Now you'll notice in my particular picture there are two z values. That's possible. You could have a ton of z values. I'm just focusing on that one z value for this particular picture. Okay, there's another one over there just to the right of A. Understand the scenario? Yes or no?
Yes.
Yes. Okay, good. So, the thing to keep in mind is once we find this average value, we end up making a rectangle here. How tall is that rectangle? Beautiful. F of z. How wide is that rectangle? B minus A. Everybody good there? Oh, you know what? I totally screwed this up. I'm so sorry. I failed you. This little guy should be colored. That's better. Thank you for not saying anything. Because I got to be inside the glass. I went crazy. I went all the way over to 0. I've had too much caffeine. I'm sorry. And I'm loving math. Okay. Right, loving math. Oh. Okay. So, two things are going on here. We've got the area under the curve of f of x. How do I represent that? The integral of f of x, area under the curve. We also have that crazy little rectangle. So think about this as puzzle pieces. If I took the two blue puzzle pieces, they should fit into the space where the red puzzle pieces are. So those two things should be the same. Which leads us to this puppy. Boom! Left side, area under the curve. Right side, area of rectangle. But since f of z is the average value, those two quantities should be the same. You all right? Okay. Smack. Oh. Okay. Doing okay? Let's take a look at an example. Here's another picture. For some reason, the math peeps like to switch back and forth between f of z and f average. They're the same thing. And also, notice that's the same formula, except divided both sides by b minus a. I personally prefer this form because it's very clear that the left-hand side is my integral area under the curve, the right-hand side is my rectangle. When you switch to this form, which many of you will do, that's okay, people have a tendency to forget to multiply by 1 over b minus a because that's just a memorization of a formula without an understanding. This, I have the understanding there that I'm finding the area under the curve on the left and I'm finding the area of the rectangle that area under the curve represents. You can use whichever one you want. That's what makes this such a great country. Okay? Let's start with something simple. I did the math for you already and told you what the area under the curve from 0 to 4 of the cubic function is. You could have done that on your own, but that's not what this is testing. You could have done that on your own, right? Okay. Good. Okay, so here's what we like to do using MBT for integrals. What is the average value of x cubed? If I take that function between 0 and 4 and I melt it down, this is commonly called the meltdown theorem. Well, it's really called the mean value theorem, but also known as the meltdown theorem because we're melting the function down. How high will that average value be? It's a matter of plug and chug. Left-hand side is the area under the curve. Okay, well, we'll do part B in a second. Yeah, let's talk about A first. Okay, so left-hand side is the area under the curve, which I calculated for you already. The right-hand side will be the area of that rectangle. Let's go back to the problem. What's B in this case? 4. What's A? 0. So that only leaves us one thing to figure out, and that is f of z. So that 1 over 4 minus 0 is the 1 over b minus a business. The 64 comes from the integral from 0 to 4 of x cubed. And that tells me that the average value of that function is going to be at 16. It's fairly tall. Any problems there? Okay, so how do I find where z is? For those of you that don't understand the question, I'll draw you a picture. Because I like pictures. Okay, so what we found is that if I go from 0 to 4 and I melt this function down, it will, by the way, do we know where that point is? It's 64, yeah. 4 to the third is 60, right? Yeah, 64. And then we know that if we melt this puppy down, it's going to level out at about this value here, which is at 6. That was weird. At 16. What I'm looking for is that z value. And notice this one only has one z value. It only hits the average value in one spot. How do I find z? No, easier than that. No, cheating. F of z equals 16. Okay. We know the function. The function is x cubed. And so therefore, we would take f of z is equal to 16, because we just calculated that. And how do I find z? I take this and I go z cubed is equal to 16. So z is equal to the cubic root of 16, whatever that is, I don't know. Plug z into the function, set it equal to the value that you find for f of z. Because we know the y value, we're looking for the x value.
So why is it z cubed equals 16?
Let me try simplifying this for you. Let's suppose you had a function Okay? And I told you what the y value is. Could you solve for x?
Yeah.
Same thing's going on here. Remember, this represents the y value of the function where it's happening. And all I'm doing is asking you to find x. So if you don't want to do that, you could just do 16 is equal to x cubed. If you don't want to get all fancies in your pansies, you could just solve for x. Z and x are the same thing. It's that point, that x value where it hits the graph. Question?
Wait, so where are you plugging in Z?
Into the original function. Yeah. You still look confused.
No, keep going.
Okay. I got just, you know, did that. Okay. Sometimes, like I said, question in the back.
But if you plug it back into the equation, isn't it just 16?
Yeah. But you don't have to plug it in. I just want to know where the x value is. Which means that this guy is going to happen at 2 point, what did I say it was? 2.519. That's the x value that gets me the f of z or y value of 16. Okay, where those two things intersect. Okie doke. Questions? I think we're all done. That wraps up section 4.4. I think that actually wraps up the chapter.
Oh, really?
Woo! Yeah.
No new notes tomorrow?
I don't know. I gotta look. I don't think so. I think practice, 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 and then some more practice.
Wow.
Okay.
So what will, I won't be here tomorrow?
I'm saddened by that information.